Um, line integrals are just a slight bit different than our regular integrals. You know, when I way back here, the integral of f of x dx, I'm integrating that with respect to x, which means I'm integrating that, like if here's my function, I'm integrating that with respect to x, and so here's a to b. What I did was, you know, chop up the a to b in intervals, right? And then, you know, do the rectangles. But anyway, that's when we're integrating with respect to x over an axis. Yeah. Very similar if we integrate with respect to y, others. But so a line integral, what's different about that is I integrate it not over an axis, but as the name suggests there, I integrate it over a line, a curve. Instead of an axis. And all right. And the we can do these in for two variable functions. So let me just give you an example here. This is what one's going to look like. So we're integrating over C, curve C, which sort of, you know, we've sort of done that sort of thing, but this is new right here. ds instead of, what do we have, dA, dV, those sorts of things. So yeah, we're integrating, so in this particular case I'm doing it over two variables. We can do it over a three variable function as well, but we'll talk about that later. So here's the deal. So I've got this two variable function, but I've got this curve C, and I'm integrating with respect to S. And if you remember, so here's curve C. So I'm integrating with respect to curve C. All right, that's integrating over that. But this ds, what does that mean? Well, that means I'm going to integrate that over, instead of, like I said, an axis, I'm integrating over that curve C. And so this ds, if you remember S, that designated arc length. We talked about arc length. Well, maybe S wasn't the letter, but that is sort of what it designates here. It's arc length, because what I'm going to do, what this means here, is I'm going to integrate over this curve C. So instead of divvying up the x-axis into intervals, I just break this up into intervals, or parts, if you will. And I'm integrating over that curve. And it's really what I'm doing is I'm integrating over each of these separately. Think about it, the arc length of each one of those, which that's really why I kind of do it that way, because remember what arc length was? This kind of comes up in our, when we go to kind of the definition here. The arc length of, we called it L. It was a to b, integral a to b of dx dt squared plus dy dt squared So we did arc length several ways. This is the arc length over the parametric curve. X equals, say, f of t, y equals g of t. That gives us that arc length. And a reason I bring that up is because basically this comes up when I go to the definition. So, and we could do more about developing this and why it comes out to be what it is, but just suffice it to say, I guess, we're going to use some arc lengths. And hopefully makes sense because, yeah, that's what when we break these up, we're dealing with some arc lengths there. All right, so here's the definition. This equals, how do we evaluate it? Well, this is how we evaluate it. We do integral a to b f, all right? So what it's going to come down to here is I'm going to need to get this curve in parametric form. If it isn't already, sometimes it may possibly be given in parametric form, but likely it is not. So we'll have to deal with that. And there's different ways of doing it. Some are easier than others, but so yeah, we're going to parameterize, if you will, x and y using we'll just call it x of t and y of t because we've already got f there, I guess. But times then we're going to do our little arc length here, the square root. You know, we went through why it is that and all that, but that comes up in this. So you do the derivative of x with respect to t squared plus the derivative of y with respect to t squared dt. Okay. So, I know, really haven't gone through the whole reason why it is, but that's what it is. Okay. So let's just do a couple and see what it entails here. Okay, so let's evaluate the integral over c xy to the fourth ds, the line integral, where c is the right half of x squared plus y squared equals 16. So the right half of the circle, semicircle, went to right. Okay, so we've been dealing with semicircles a little bit, but this is a little different because what I want to do, this integrating this line integral, I need a parametric form of this. In other words, x equals, some function of t, y equals some function of t. All right, you with me? So I need to parameterize this. Well, like I said, there's several ways. Sometimes, you just say, like if you've got, y equals x plus 4, you can just say, well, x is t and then y is t plus 4. Sometimes it's that easy, but in this case, a little, and we could maybe come up with other ways, but here's it turns out for a circle, you can parameterize it by saying x equals r cosine t, y equals r sine t. And that gets the whole circle. Now we'll deal with being the right half in a second. So you see, in this case, our r is 4, right? So what would x be? 4 cosine t. And then y is 4 sine t. And so that's, for a circle, a way you can parameterize it. We've probably done that, but it's been a while. Okay? Now, to get just the right half, that means I'm going to have to limit t here, and that kind of gives me my a and b, if you also. So what values of t would give me the right half of my circle? Well, I would go from this t, which negative pi over 2, all the way around to this t, which would be positive pi. Okay? With me so far? Good? All right. Now, what I do then, so what this basically says is I'm going to parameterize basically all this, or I parameterize my c, and so I also changed in, so now this again gives me my a and b, so t is my parameter, and that's what I need my values to range from. All right, now x, well, x is 4 cosine t. So we got 4 cosine t. Y is 4 sine t, so that means I have 4 sine t to the 4th. So you're just changing whatever your parameters are, you just change whatever that tells you to do. All right? Then the rest of it, all right, so the rest of it, so that was this part of that. So the rest of it is you do the square root of the derivative squared. All right, so the derivative here, so dx dt here is going to be what? Negative 4 sine t. So I do that squared. And then the derivative here is 4 cosine t. So I plus the 4 cosine t squared. And then dt with so just f of x of t, y of t, that just, just plugging in whatever x is and whatever y is, depending on what that equation or function is. And then do your derivative square root. All right, well, so then it's just a matter of evaluating. So the good news here is it's just a single integral. If that is any good news, I guess. But all right, so what do we got here? Negative pi over 2, positive pi over 2. Let's see, basically I have 4 times 4 to the 4th, that's 4 to the 5th, which is 1024. Cosine t, sine 4t. And the good news on this, all right, so that'll give me 16 sine squared t plus 16 cosine squared t. Do you see what's going to happen there? If I factor off of 16, I'll have sine squared plus cosine squared, which is 1. So this part here is just going to be the square root of 16, which is 4. So we have another 4 added, 4 to the 4th, 4 to the 6th. So this is all just going to be, so that's 1024 times 4096 cosine t sine 4t dt. So I won't say all of them work out pretty nicely, but they try, I guess, usually to make it, the integral come out pretty nicely, but this one's just a little u substitution. U equals sine of t, and then du would be cosine t dt. And so you've got, that would just be u the 4th du, wouldn't it? With me there. So it's just 4,096, so it'd be u to the fifth, so that'd be divided by 5, u to the fifth, but u is sine t, so it'd be sine of t to the fifth. I'm going negative pi over 2 to positive pi over 2. That'd be 4,096 over 5. All right, so if I plug in pi over 2, that's 1. So you have 1 to the fifth minus sine of negative pi over 2 is negative 1. Negative 1 to the fifth is negative 1, so you'll have 1 plus 1, 2 times 4,096, which is 8,192, isn't it? How's that? Not too bad, right? Okay. Here's another one. Another possibility, what could happen as far as parameterizing. Okay, so let's evaluate the integral over c for x cubed ds. In this case, we don't even have a y, but where c is, as this little diagram shows. It's a little complicated, you might say. All right, so negative 1, negative 2, negative 1. Positive 1, positive 2. Okay, so here, all right, so we start here at negative 2, negative 1, and just go straight across. And then at negative 1, kind of bend up, not straight. You got a little bit of a curve there, and then it goes straight up until we get to 2. So what this one is, all right, so we don't have to have just a single curve or a curve that can be represented by a single function. We can have a curve here, so C is going to be made up of 3 parts. We're going to have C1, C sub 1, and C sub 1, well, it goes from negative 2 to the y, I mean the x, but that's just a horizontal line. It's y equals negative 1. This curve, you can't probably tell, but C2, part of C, that's going to be y equals x cubed minus 1. And then C3, well, C3 is just a vertical line, it's x equals 1. Okay, so we can have 3 different parts, or other number of parts. Is the example here I'm showing. Okay, well, again, the first step is you want to parameterize the curve. Well, in this case, we parameterize the curve by parameterizing each part. And over here, we just had to parameterize, that one curve. In this case, we've got to parameterize 3 parts, and these are maybe a little easier than that first one. All right, so C1, writing that as a big one, but C sub 1. So what we're saying is, I need to write this as an x equal y equal function of t type parameter. Parametric equations. Well, y is likely to be negative 1, so there's no change in that. And the deal is the x then, well, the x will just be whatever t is, as long as I put t in the proper frame here. So if t goes from what, -2 all the way to 0, that would give me that line right there. Not too bad. All right, and C2. All right, C2 is a little easier. Like I said, this one's like the one example I gave up here. I've got y equals x cubed plus 1. So in that case, I'm going to let x be t. And then the y is just t cubed minus 1. All right. That would be that same equation. All right, and then the other thing, the only thing there is what values of t would be. Well, t would go from what, 0 to 1, same as the x. Is that okay? So far, so good. And then C3, well, C3 is a lot like C1, except we've got x is 1, so the y is the one kind of varying. So what would the values of t be on that one? So they would need to correspond to the y values, right? So y goes from 0 to 2, so it's another 0 to 2 there. How's that? A little different. So when I evaluate, I'm just going to evaluate 3 different intervals here. And then C is the interval over the whole C, and just those added together. All right, so we're going to integrate for C1 first. So that would be the integral. So I change my function based upon this. So x is t, so that'd be 4t cubed. Then it's times the square root of the derivative squared. That would be 1 squared. The x plus the derivative of the y with respect to t, that'd be 0. So this is going to, and so t then ranges from -2 to 0. So some of these turn out to be very simple integrals because that's just going to be 4t cubed, isn't it? Which is just t to the 4th, right? Because the 4's would cancel. And -2 to 0, so that'll be 0 minus 16. Is that right? Is that right? 16. Then the integral for C2 of this thing, well, it'll be the integral. The t's are going to go from 0 to 1 on C2. X cubed for x cubed, well, x is t again in C2, so it's still 4t cubed. And your integral, the derivative, so again, the derivative of that would be 1. And the derivative of that, the y's would be 3t squared. So I'd have to do 3t squared. Ooh. And that's pretty nice. Because look what happens there. That's the integral 0 to 1 of 4t cubed square root of 1 plus 9t to the 4th. See, that works out nicely because it's u substitution. U equals the 1 plus 9t to the 4th. du then would be 36t cubed dt. So that's going to turn into the integral of 4t cubed square root of u du over 36t cubed. So that gets rid of it. That's 1/9 basically square root of u. The antiderivative square root of u would be u to the 3/2. So it'd be 2/3 u to the 3 halves, but let's go back to u is 1 plus 9t to the 4th. And so we're nicely evaluating that from 0 to 1. So we get 2 27ths, plug in the 1, we get 10 to the 3 halves. Then unfortunately plug in the 0, don't get 0, we get 1. So, unless you want to round it, that's your, the first one's negative 16, the second one's that mess. But. And then C3, 4x cubed, so we're doing the same integral each time, it's just that our curve part is changing. All right, so, okay, so in C3, we're going 0 to 2, 4, and then x is 1, so that part is just 4 times 1. Then we have to do the square root of the derivative. So the derivative of x, derivative square, sum of the squares, the derivative I should say. The derivative of the x, well x is 1, so the derivative is 0. And the y is t, so the derivative is 1. So that works out pretty nicely. Square root of 1. So the integral is just 4 et, 0 to 2. Just 4t, 0 to 2, which is 8. So the integral, the full integral, 4x cubed ds over c, then it's just these three added together. So it's negative 16 plus this plus that. At least combine the 8s, I guess. 8 and negative 16. I guess we throw in the minus 2 27ths too, but something like this. I guess that'd be negative 8, 2 27ths. All right. Question or concern?